Okay, what I want to do in this video is give a little bit of a brief introduction to limits, just we're going to get a working understanding of limits. A lot of calculus teachers start off their calculus course by dealing with the limits and learning how those work. Theoretically, that's the approach to do. Practically, I think that the limits are a little bit too technical, and it makes the calculus seem a lot harder than it really is. Limits, we're going to deal with it from an intuitive perspective to begin with, and then I'll give them a more in-depth treatment in Calculus 2. We're actually going to wait until Calculus 2 to deal with the limits in a very technical way. For now, we're just going to talk about the limits in an intuitive way, and that's why I need to make this video, is that Sal assumes that you already have some background with the limits, and actually we haven't. We're jumping straight into the derivative. Okay, so what Sal's doing here is he's trying to find the slope of a tangent line. Well, the problem with trying to find the slope of a tangent line is there's only one point that meets our curve, and slope requires 2 points. Right? We need change to be occurring, change in y over change in x. We need 2 points for that to happen. So since there's just 1 point on the tangent line, we're sort of stuck. We're stuck unless we are able to use the limits. And what we're going to do here is we're going to look at the slope of the secant line. That's not going to be the same as the slope of the tangent line necessarily, but it should be a good approximation. Right? And a tangent line just barely grazes the graph. It goes in the same direction as the graph. The secant line meets the graph at 2 specified points. And that's what it means to be a secant line. Okay? So if we compute the slope of that secant line, as long as those points are somewhat close together, that slope is approximately the same as the slope of the actual function, of the actual graph. Now, to get a better approximation, we would just let the 2 points come closer and closer together. And if I want the slope at this 1 point, I take the second point and I bring it in further, or bring it in closer and closer here. What that amounts to on the x-axis is I take this x value and move it to the left more. In other words, I'm decreasing h. H is the distance between these two values, or the difference between these two values. I'm going to decrease h, get it closer to 0 so that these 2 points are closer together. And then the slope of the secant line will be a better approximation for the slope of the tangent line. Now the way I denote that algebraically is I say I'm going to take the limit as h approaches 0. That means that I want my h value to get closer and closer to 0 and see what happens. Now ideally we could just plug in 0. That doesn't work here though, because if I plug in 0, I actually divide by 0. Which sort of makes sense that it doesn't work. Just like we talked about, if my line only has 1 point that I know, okay, then I can't compute the slope. My delta x is 0. All right, and that's what's happening here when when we try to plug in h is 0. So this is saying that we're going to find the derivative, or the slope of the secant, or the slope of the tangent line, by taking the slope of the secant line and computing the limit as h approaches 0. In other words, see what happens when h gets closer and closer to 0. Now here we can't actually find out exactly what happens because we can't plug in 0. We'll divide by 0. What we need to do with these limits is do some kind of algebraic manipulation so that we can cancel out this h and get that. Actually, if we plug in 0, we get a allowable value and not something undefined. And we'll see that happen in the derivatives 2 video. In the derivatives 2 video, we're computing the slope of the tangent line of y equals x squared at x equals 3. Okay? And that's this green tangent line here. Well, we get at the slope of the tangent line by computing slopes of secant lines, like this red line. Okay? So the slope of the secant line, Sal has computed over here, and we're leaving delta x general. Delta x is playing the exact same role as h was over here. Okay, we're going to leave delta x general so that we can move this point closer. Okay, we compute the slope of the secant line, and he gets down to 6 plus square root of x. And this is great, because what was on the denominator canceled. Okay. Now we got that the slope is 6 plus delta x, I think I said square root of x earlier. It should be delta x, 6 plus delta x, and we take the limit as delta x approaches 0, because we're wanting the slope of the tangent line, the derivative, not just the slope of the secant line. Well, in this case, we can actually plug in 0. So, since we can plug it in, we go ahead and do that. 6 plus 0 is 6, so that means the derivative of the function at x equals 3 is 6. In other words, the slope of this tangent line is 6. Okay, so that's what I want you to take away from this video. When you're dealing with a limit, what you want to do is just plug in this number for that variable if you can. Okay? If you can't, do some algebraic manipulation like we had to do over here with what we started with. Okay? Do some algebraic manipulation until you can. All right. Okay, so I hope that this helps to clear up a little bit about the first two videos. Please, please, please come into my office hours. Please shoot me an email. Please get a hold of me if you would like help, if you need something explained concerning these videos. This is my job, and I want to help you out. I don't want you to fall behind, and especially this early in the semester. I want everybody to be on the same page. I want us to all try to keep up. So please do let me know if you need any help. I'm happy to help you.